and that has to do with simple statistics and correlation, and hopefully this is a little bit more practical and helpful. So we're going to try to explain why you do this. So simple statistics, this is sometimes where students kind of trip up a little bit. Let's just give you an overview. I mean, many of you probably had stats. I'm going to give you a little bit more practical application here. So correlation, we often try to correlate data. There's an old saying, you know, correlation doesn't necessarily mean causation. That happens over and over again, from COVID to other systems, where people see a correlation and say that must be the cause, and it's not always this way. So let's see how we can figure this one out. So let's do simple things. A simple statistical analysis has to do with averages, for example, and a standard deviation. It can tell us a lot about the data we are collecting if we do this one, and we stick with the basics. If it gets more complex, there are other statistical methods you can use. However, I found it easier. I'm a very visual person. If I have a complex statistic, to use some kind of a graphical approach, because I can see, hey, data matches, or sucky, it doesn't match, right? Right. So how are we going to do this? First of all, average and standard deviation, you already know how to do this. If not, your calculators or your computers have little buttons that will do it for you. But what do they tell us? So what is the average, often shortened AVG, or also mean? What does it tell us? So the average is basically a model of your data set. It approaches the most common value. Remember when we talked about accuracy, we're approaching the most common value, or the accurate value on this one. That's what the average tells us, right? It also has a way of minimizing error when we try to predict certain values, because it all concentrates of the most likely culprit that it could land on. The average works fairly well. It actually works incredibly well, unless you have outliers. Now, and you sometimes can do a visual analysis of outliers. If you graph it and your points plot nicely in a row or in a curve, and one of those suckers is way far out in the left field, you might want to eliminate that one and pretend like this measurement has never happened. Now, if you have a lot of outliers, you cannot do this. But if one really is out, is that maybe I was asleep in the switch, or maybe I sneezed in my test tube, or something happened there. So if you have a data set of 50 data and maybe you have 2 outliers, you may be thinking about, and you can kind of try to play around with it a little bit. What happens to my data when I remove those 2? And maybe it would be better to run my data without those 2 outliers. Okay, so what's standard deviation of an STD? It's one of the common abbreviations for this one. So this is a measure of data dispersion around the mean. In a way, it approaches that high-low value that we used for precision analysis. Little bit better, but it tells us this the spread. It's basically the spread, or how tightly are your values bunched around your mean. What does it mean is, if you have a small standard deviation, it means your data starts to cluster around a common point, around the mean. That's your common point. And if you have a large standard deviation, then your data starts to disperse over a greater area. And if you have too much of a standard deviation, it means, can you really tell with absolute certainty that 2 means are separated from each other? I mean, if your standard deviations overlap, then you're going to have a problem with that. Just to give you some background here. So practically, how can you do this? Why not use Excel? Excel has all these functions built in. It's incredibly cool. And we're gonna watch a little video. I don't have to recreate this video. It's a pretty good explanation of how to use Excel to calculate your averages and standard deviation. So we're gonna launch this video.
This video is going to show you how to calculate the average and standard deviation using Microsoft Excel. The dataset we'll look at has the snowfall in centimeters over the past 10 years, and you can see the dataset below. To begin, you're going to double-click in an empty cell and type in the equals sign to start our equation. You're then going to type in average. In the drop-down menu, you're going to select average, and now we have to input our data into the formula, so we're going to do that by clicking and dragging down for all of the data set. We can now look at our formula. We need to close the bracket and press enter to do that calculation, which means the average snowfall is 303 9/10 centimeters. For the standard deviation, double click in an empty cell and type in equals. Then you're going to type in STDEV, which represents standard deviation. You can see we have a bunch of different options. We're going to select standard deviation S, which stands for our sample. Now we have to select our sample. So double click that, and we're going to select the data to input into that formula by clicking and dragging down all of our data set. Back to our formula, we need to type in close bracket and press enter to do that equation. Now this tells us that the snowfall in past 10 years, the average snowfall was 303 9/10 centimeters, and the standard deviation was 61.10 centimeters.
So, little overview over this whole thing. Gives you some idea. Collecting data. A little bit about collecting data. We talked about it and some experimental results. Graphing, a picture is worth 1,000 words. So graphing is really a good way of telling what you have measured and figured out. And if you need to write reports, one good way of doing it, do your graphing, your pictures, your illustrations first, and then write the report around your graphs. It writes it so much easier because you can reference now the graph at all the time. Okay, so there are, of course, several graphs you are familiar with. The bar graph is an old favorite. Some of you have done those. Line graphs are also popping up, and you've probably done those, and XY graphs. And we're going to try to explain the difference. Where would you use a bar graph, or would you use a line graph, and where would you use an XY graph? And well, let's try this again. Let's do a simple graphical visual analysis of my data set, right? Question, are my two data sets related? And in order to do this, I really need to plot an XY graph, or scatter plot, as they would say it. We have two numerical data sets. So in this case, what you can see is my dots go all over the place. There seems to be no rhyme or reason with these green dots plot. And therefore, I can say there's really not much of a correlation going on. So it looks like these dots are not necessarily related. Well, what about this one? That's kind of cool. All my dots plot more or less in a nice straight line. So here I have what I would call it a linear correlation. They fall onto a line. That is really helpful. Just a visual. Don't even need to do much math, just looking at it. Here's a curve correlation. So it's a nonlinear correlation, but I have a curve that appears here. And that's always really nice. By the way, scientists love straight line correlations. And this is why if you have a curve, what often happens more in hydrogeology than in mineralogy is you're trying to make a straight line out of it by forcing one of the data sets into a logarithmic scale. And that often straightens out the graph, and then you have a straight line, and then you can come up with some mathematical solutions in this case. Okay. You can also have something that is hard to express with a mathematical formula. It's a cluster correlation. All my data seems to be bunching up in one corner of my graph. They're definitely somehow related because they're starting to cluster. And I can see this visually quite well. All right, so using graphs, little bit is this one, making an XY graph. Remember, straight line is a preferred one. You need to have some data pairs, and you plot one set of the data on the x-axis, and the other set you're going to plot on the y-axis, and then see what you're going to get for a result. Remember, you need to use an XY scatter plot for this. So here I have my data set plotted. It looks like I have two outliers. Question is, should I eliminate those maybe to get better data? This one especially is kind of odd. It's judgment call. I often play around with both and see what's happening. Okay. So correlation is how do things match up? There is a numeric measurement we call the R factor. And the R factor tells us how well our data set is linearly correlated. I'll give you some examples. Here I have a perfect positive correlation. All these little dots are like pearls on a string. I have the best R factor possible. It's a 1. A 1 equates to 100%. So I have 100% correlation of these two X and Y data points. So now, what about this one? Well, in this case, I can try to put a straight line through this whole thing, like the best fit. But there's so many dots that are off that straight line. So my R value, my correlation value is going to be less. It's not an exact straight line like over here. I'm going to get maybe half of the dots live close enough that they even get close to this straight line. And so 0.5 would maybe correlate to 50% of a linear correlation. If I go to this picture, now they are not even, these are at least clustered here. There's no rhyme or reason. They are all over. So it looks like I have no correlation. If I try to make a best fit straight line, well, your guess is as good as mine. I can put it like this or like that, or maybe even horizontal or vertical. They're all the same. So in this case, I have 0% correlation. Now, what if my perfect line goes the other direction? Then I have a perfect negative correlation, or a minus 100% correlation, -1. And this is called an inverse correlation. So positive correlations and negative correlations are both good. If a few of those outliers are here and there, then of course I may have a 90% correlation and 95% correlation and so forth. So it tells a little bit of how well these are correlated. Again, Excel graphing is pretty good. There are many excellent online tutorials for how to create a graph in Excel. It saves you a lot of work. There are 3 main types of graphs. We already explained it: bar, line, and XY scatter plot. Know the difference between a line graph and an XY scatter plot. It plots the data differently. So I'm going to have 2 values here on my little column, A and B, and see what's going on. And the first plot here is a line graph, and you can see what's going on in a line graph. What if I did the same and plotted that in an XY scatter plot? My graph looks different. What's going on? Well, in a line graph, I use it when one of the data sets, in case this one, can be treated as a label. They may not be inherent values. It's just a label, like the 22nd of February, 22nd of February, 22nd of February, something like this, maybe a day of the month. So if they can be treated as a label, I would do a line graph. However, if these are actual measurements, like temperature versus millimeter water column, something like that, that I get on a readout, then I would plot it as an XY graph, and I would get actually the data results like comparing two numeric measured values against each other. So in most cases, you probably do not want a line graph. Know this when you plot data. We do a lot of data plotting, hydrogeology. There's a little bit of kind of analysis in mineralogy, not terribly much, but you need to know these the differences between those two. Most of the time, I tell you right now, you want an XY graph, right? Use when both data sets are numeric and have specific values. That's what we want to do. All right, good. So predicting the future, this is always great. Math and modeling. So we are modeling data. We're trying to predict something. So a curve, any type of a curve, can be described by a mathematical formula, a mathematical equation of some sorts. Again, scientists like straight lines. If we can get away from a curve and make a straight line, that would be better. What does it help me? Well, here's number one is, if I have finally figured out a curve or a straight line, I can calculate any point on the graph even if I do not have a data. And figure out, so what happens if one data set is this? What should be the other one be? Or I can calculate areas of the graph that are not shown, something way outside of the graph. Maybe my graph goes to the year 2020, but I would like to see what happens in 2025. That's outside of the graph, but if my graph holds steady, I can predict what might happen in 2025. So it can go way out there. Okay. So formula or equation of a line, the generic formula of a line is y equals mx plus b. A lot of you are familiar with this one. What do these little things mean? X is my independent variable or data you would plot on the x-axis of your graph. Well, duh, okay. My b is the y-intercept, or where my graph, my straight line graph, remember this is linear, that's my straight line graph, would cross the y-axis. At what point would it do that? My m is the slope, or how steep my graph tilts. Very something easy to remember, rise over run, slope of a hill. Same way that we do here on that particular graph. And y is the dependent variable, and a dependent variable means this is your answer. So if you plot in x and know the rest of them, then you can spit out y on the other end. So here we're going to try this. How do you get an equation for a linear graph? Those of you who have a background already know this. Maybe you can help tutor some of us who have questions, but how do you get a equation for a linear graph? So it's my linear graph. You see the data set down there. And what does it do to get the slope, or m? What do I need to do? Well, I'm going to take any two XY data sets, like one here for X and two for Y. I'll use this point. 1, 2 works. Or a 6 here and a 5 over there. Remember, I always write the X first. So 1 to 2 or 6 to 5. Well, X, Y. Okay, so pick any two. Doesn't matter. Pick two. Sort by highest X first. So in this case, the 6 here is my highest X. I'm going to write this one first. 6 and for the X and 5 for the Y. And then there comes the next one. 1 for the X and 2 for the Y. Next step, subtract my X from X and the Y from Y. So I had a 6X and the 1X. So 6 minus 1 gives me a 5 right here. And in this case, my y from y, 5 minus 2 is a 3. So I get a 5 and a 3 right there. Now, divide my y by x. Okay, my y is 3. my x was 5. So 3 divided by 5 gives me, if I want to do it as a decimal, a 0.6. And a 0.6 is the steepness of your slope, or m is 0.6. Now you might get a negative number, depending which way the graph tilts, but that is the tilt or the steepness of your slope. In a sense, it's kind of a 60% slope. Okay, so this is how you get m. All right, let's do this again. How do you get the point where my graph intercepts the y-axis? It's called the y-intercept, or the b for my equation. So either the y value in your table where x equals 0, if I have that, sometimes I don't, or you first get m and then solve my equation for b. What do I mean by this one? Well, I had the equation y equals mx plus b. Now you need to solve the equation for b, that b is all by its lonely self on one side of the equal sign and all the other symbols on the other side, and that becomes b equals y minus mx. Well, what are you going to do now? Plug in any x or y pair into that equation. You have the m, 0.6, and they all should give you the same result of whatever b might be. Looks like around 1.5 there. We'll get something like that. Okay, so what's my equation? Well, the slope or m was 0.6. My y-intercept of b, if I calculate it out, was actually 1.4, almost close to 1.5. So the equation for this particular graph is going to be y equals 0.6x plus 1.4. Why are we doing this one? Because now, if you have not enough data points or you want to predict what happens if this number down there is a 12, now what would be my y value? My x value is 12. It's outside of the graph. Now I can plug it into the equation and I can start modeling. This is the very simplest form of making a mathematical model of anything. Geologists in particular, if you cannot see something, you make a model and try to somehow visualize it. And often this is where these linear equations and graphing comes in as the simplest form of a model.